So Amir, Gilad is going to be the next speaker, and his talk is on the accessibility and privacy of provenance-based explanation. Amir, you cannot hear it.
Maybe still on Daniel.
You muted them.
Yes, yes, okay, great. Now you can hear me?
Yes.
Okay, so this talk is going to be based on collaboration with Daniel, Yuval, Nave, and Ariel. So we know that provenance is an incredibly useful tool for understanding processes that involve data, debugging the data, justifying the query result, etc. However, in its raw form, it may be unusable in for certain situations. So, for example, provenance can be very long and complex, like in this polynomial, and this can make it difficult for users to parse and understand it, especially if they're not experts. Second, provenance can also be too revealing in certain applications where the query needs to remain confidential. So for example, showing provenance-based explanations can reveal the underlying query that generated them. So in this talk, I want to discuss different post-processing options for provenance to make it suitable for specific applications. So I'll talk about two works, and I'll do it in two parts. In the first part, I'll talk about provenance explanations in natural language and how we developed a specific mechanism for provenance factorization and summarization for such explanations. In the second part, I'll talk about abstracting provenance for the sake of maintaining the privacy of a confidential query. So both uses of provenance involve some sort of provenance manipulation to make it suitable for the specific usage. So let's consider the first scenario where we aim to make provenance-based explanations accessible. So we know that it's usually difficult for users without technical training to query the database, and even experts sometimes find it hard to formulate a query that they want, since they have to know the exact schema of the database. So this is where natural language interfaces come into play. Such interfaces allow users to ask their queries in English and get the results. So let's see a use case. So let's consider this natural language query over an academic research database. Return the organization of authors who publish papers in database conferences after 2005. When this query is inputted to a natural language interface, it's translated into this formal query, which is then evaluated over the database, and the results are shown to the user. Now, one of the results is Duke University. A user who gets this result may now wonder, why is this part of the result set, or why does it answer the conditions they specified in the question? So what we would like to show is a clear and concise natural language explanation for the result, like this one. Duke is the organization of 63 authors who published 170 papers in 31 conferences in 2006 till 2015. So I'll quickly demonstrate our provenance model. So reconsider this natural language query. So this is the formal query. When it's evaluated over the results, we consider a value level provenance. So here we see the provenance polynomial, where each monomial represents a single assignment that resulted in the result Duke University, and it's composed of pairs where each element is the variable, and the second element is the value to which it was mapped to by the assignment. So for example, here we see the assignment, one of the assignments leading to the result Duke, and the colors denote some of the variables from the database mapped to the values. So not all variables appear in this polynomial for simplicity. So now let's go back to our problem. And when we tried to solve the problem, of translating raw provenance to natural language explanations, we tackled two main challenges. The first is that the formal model of provenance is very far from a natural language sentence. And second, the provenance of even a single result can be very long and convoluted. And we use the structure of the input question to tackle both challenges. For the first challenge, we use the structure of the input question as the basis for the structure of the answer. And for the second challenge, we shorten the provenance by factorizing it and use the input question as a criterion for generating only factorizations that are suitable for natural language answer generation. So I'll quickly go over our framework. First, the user inputs a natural language question into a natural language interface. In this case, we used an Amir, which is based on a 2015 VLDB paper. Amir then parses the input question, generating a dependency tree, and it also maps the words of the questions to tables of the database while translating the question into a formal query. During this process, our augmented version stores both the dependency tree and the mappings from words of the question to variables of the query. The formal query is then evaluated using the provenance-aware evaluation engine, CELPI, which is based on our 2015 VLDB paper. And once we have the provenance, the results, and the mappings, we factorize the provenance and either generate a sentence based on the factorized provenance or further summarize the provenance and then generate a sentence. So let's demonstrate the explanation generation process for a single assignment first. So on the left, we see the dependency tree of the question with the mappings to pairs of variables and values from the database. For example, the word organization was mapped to the variable oname, which was mapped by the assignment to the value Duke from the database. So once we have the dependency tree and the mappings, we would like to convert them to an answer tree in order to make an answer sentence. So we now consider the part of speech and relationship of the words in the question given to us by the dependency tree also. And based on this information, we augment the dependency tree by either adding the mapped value as a node in the tree or replacing the mapped word with the value mapped to it. So for example, the value Duke, which was mapped to the word organization, is added as its child, while the value Junyang replaces the word authors to which it was mapped to. So once we have the answer tree, we convert it to a sentence by reversing the mappings from words to values and considering the location of the words in the original natural language query. So based on these and the answer tree, we generate the sentence, Duke is the organization of Junyang, who published iCheck in Sigmod in 2014. So now let's consider the general case where a single result can stem from multiple assignments. One possible solution is to generate a separate sentence for each assignment. However, this would result in a long explanation that would be difficult and tedious for the user to read. So instead, we employ the already known concept of factorization, which is similar to the concept discussed in previous talks in this workshop. And we generate a single sentence containing all assignments. So consider the provenance polynomial that we've seen before, but this time we only show the values. Here are two different factorizations of this expression. The left one is the shortest factorization of the expression, and the right one is a longer factorization. Now, the standard in previous work has been looking for the shortest factorization, since it's the best solution in terms of storage of the provenance. But recall that our goal is to generate a natural language question. So is the shortest factorization the best solution in our case as well? And here's a hint. The intuition here is that we want a factorization that follows the structure of the input question, so it'll be easier to generate an answer sentence from it. So let's reconsider the natural language question that we had, and the factorization that we've just seen, the shortest factorization. So at the bottom here, we see a reasonable sentence based on the structure of the factorization. So first note that this is not a clear sentence. And what's more, the red parts are not part of the question, so it's not clear how to automatically generate them. So let's see what happened. On the right, we see the dependency tree of the question, and on the left, we see the factorization. Now notice that the word authors is an ancestor of the word conferences in the tree. However, in the factorization, the value Jun Yang, which was mapped to the word authors, appears lower in the hierarchy than the value Sigmod mapped to the word conferences. So the hierarchies are reversed, and the structure of the factorization is disconnected from the structure of the input question. However, if we consider the longer factorization that we've seen, this factorization maintains the hierarchies between the words of the original question, and we get a clear sentence for it based on the structure of the question. So a factorization that maintains these hierarchies is called T-compatible, since it is compatible with the dependency tree. So therefore, our algorithm uses the dependency tree as a guide to obtain T-compatible factorizations using a greedy approach. We traverse the dependency tree from top to bottom, and for each level of mapped words, we take out the values mapped to these words, prioritizing based on the frequency of the values at each level. So the complexity is n squared times log n, since we have to traverse all n nodes, and for each level of mapped words, possibly sort the values according to the frequency. And we get the guarantee that this algorithm will generate a T-compatible factorization that can be transformed to a natural language explanation. So now an answer based on a factorization can still be too long at times. So we can shorten it even more using provenance summarization. We build on the provenance factorization that we generated in the previous step and choose the level at which we want to summarize. We assume that we have a summary functions for each value type that we can apply to the values. And if we choose a specific level, we summarize all levels below it to ensure that we get a T-compatible summarized factorization. So choosing a higher level means that we get a shorter but less informative answer, like with the brackets A. If instead we summarize at a lower level, like with the brackets B, we would get a longer answer containing more details. For example, the author names. And users can experiment with different levels of summarization. So to assess the quality of our system, you can see a few examples of the questions and the answers and explanations that our system provided. We've also asked in our paper for external users to formulate their own queries and examine the explanations that they got. So, for example, for the question, return the authors who published papers in VLDB before 2016 and after 2007, we got the summarized answer for Tova Milo. Tova Milo published 16 papers in VLDB in 2008 till 2015. So now I'd like to talk about a different problem, and this problem relates to abstracting raw provenance for maintaining the privacy of a confidential query. So consider this scenario. A company performs a proprietary query over a database to determine whether a user should be targeted for an ad. The user is then shown the ad, and if requested, also a personal explanation for why they were shown this ad. So this scenario has been addressed to some extent by large companies trying to provide explanations for ads. So suppose, for example, that James and Brenda are shown an ad for a dance music album, and they'd like to know why. the system can provide each of them with a personalized explanation based on their data. So for James, it's the fact that his hobby is dance according to Facebook and he's interested in music according to WikiLeaks. For Brenda, it's the fact that her hobby is dance according to LinkedIn and she's interested in music according to Facebook. So now let's assume that James and Brenda are friends and share their data and explanations. So we can model this scenario with a small database representing a database for the information about social networks. So it's composed of 3 tables. The right one shows the ID of each person. The middle one shows for each person ID, their hobbies according to different sources. And the leftmost table shows for each person their interests according to different sources. So the problem now is that James and Brenda can reverse engineer the general criterion on the basis of which the company decides to show the ads. In fact, our previous work has shown that in many practical cases, it's enough to show only a very small number of provenance-based explanations to successfully reverse engineer the query. However, if we keep the explanations at a higher level, reverse engineering the general criteria would become more difficult. So in our example, if we tell James that the reason he was shown this ad is some information from Facebook, and it was published on WikiLeaks that he's interested in music, and tell Brenda that the reason she was shown the ad is due to some information from LinkedIn, and because she's interested in music according to Facebook, this would make it more difficult for James and Brenda to detect the underlying query for showing this ad to people. So let's shortly discuss our model. So here again, we see the database tables that we've seen before. Below them, we see the formal query. Now, in general, we consider UCQs, but we can extend our models to aggregate functions as well. And the query will return the IDs of people whose hobby is dance according to some source and whose interest is music according to another source. So here is one satisfying assignment to the query that yields James's ID with color-coded tuples to show the satisfying assignment. So in this case, we model the provenance using the NX semiring, which is the product of the IDs of the tuples. But in general, we can support other commutative semirings as well. So we assume that this provenance is the basis for the explanation shown to the users. So now we can define what is a provenance example. So recall that James and Brenda both had different explanations that they shared. So the model, to model this, we use a table with 2 rows, and each row contains the output of the query, along with the provenance generated by the query while producing the output. So now I'd like to talk about provenance abstraction. So this concept has been considered by previous work as means of reducing the size of the provenance to make its storage more efficient. So here we'll use it for a different purpose, namely to make the explanations more vague. So reconsider the 3 database tables that we've seen before and the tree below them. This is an abstraction tree that groups tuples in the database according to their source. So for example, the tuples I3, H2, and H5 were obtained from LinkedIn, so they're grouped together under the node LinkedIn in the tree. The nodes Facebook and LinkedIn are then grouped under the parent social network. And this is just one example of such a tree. In general, there can be multiple options for such abstraction trees, even for the same database. So now let's consider the abstraction tree that we've just seen. And below is the provenance example representing James and Brenda's explanation for the ad. We can make the provenance in the example abstract by replacing some of the tuple identifiers with one of their ancestors in the tree. So in this example, we replace H1 with Facebook and H2 with LinkedIn. So now that we have an abstract provenance example, notice that there are several tuples that can replace each of the symbols Facebook and LinkedIn. So namely, these are the children of Facebook and LinkedIn. Therefore, there can be several queries that generate the provenance and output the corresponding ID. So here are 3 examples of such queries, and all 3 will generate the output of the provenance that can be abstracted to the one shown on the slide. However, since we know that James and Brenda are intelligent users, we can't fool them with just any set of queries and think that they'll fall for it. So the dummy queries or the candidate queries need to make sense if we want to hide the real query. So this is the reason that we have criteria for the candidate queries. So first, each query needs to be connected. So every predicate in the query needs to share a variable or a constant with another predicate in the query. So in this case, all 3 predicates share the variable ID. The queries also need to generate concrete provenance that can be abstracted to the provenance in the example when generating the output. So this property is called consistency. And third, the queries need to be inclusion minimal. That is, no other consistent query is contained in such a candidate query. So this ensures that the query is a tight criteria.
Amir, you have about 5 minutes left, okay?
Yes. Okay. So if k such queries fit the abstract provenance example, we say that its privacy is k. So when we abstract the provenance, we gain privacy, but we lose specific information about the provenance and hence the explanation. So every time we replace a tuple with its ancestor, we have multiple ways of interpreting the provenance. So consider the abstraction tree that we've seen and this abstracted provenance example with the symbol I1 replaced by Reddit. There are 4 ways of making the provenance concrete again, and this defines a probability space over the set of possibilities, where each possibility has a probability associated with it. So to quantify the loss of information, we use entropy over all options to make the provenance concrete. So now we're ready to define the problem that we want to solve. And the problem is to find the optimal abstraction. And more formally, given an abstraction tree, a provenance example, and a privacy threshold k, we want to find an abstraction for the example that achieves privacy at least k and incurs the minimum loss of information over all abstractions that achieve the privacy threshold k. So this problem turns out to be NP hard, and this can be proved by reduction from vertex cover. So to nevertheless find the optimal abstraction, we do iterate over all possible abstractions, but we can eliminate most of them quickly using practical optimization. So here we see the abstraction tree and the provenance example that we know. And here are several abstractions that we start to iterate over. So we can quickly eliminate the first one since it does not meet the privacy threshold, and we don't actually need to generate all the queries to see that. And the idea behind this optimization is computing the privacy row by row and removing the disconnected queries along the way. So we can then eliminate the second abstraction since it does not minimize the loss of information compared to the leftmost abstraction. And we continue in this way until we get the optimal abstraction. So the guarantee of this algorithm, simply by the property of iterating over all abstractions, is that it returns an optimal. So here's a sample of the experiments that we conducted. And here we measure the runtime as a function of the privacy threshold for a TPCH and IMDb dataset and queries. And we see that increasing the threshold even to 20 does not significantly increase the runtime, showing the performance of the algorithm. So to summarize, we've seen two different ways of manipulating provenance to make it fit natural language explanation and for maintaining privacy. We've shown that we can factorize and summarize provenance to make it understandable and concise for explanations, but also we've shown that we can abstract provenance to make it preserve the privacy of queries. So our tools were the dependency tree for natural language explanations that served as a guide for generating suitable factorizations, and the abstraction tree, where we used it as a guide for generating private provenance. So we also talked about the trade-off when summarizing or abstracting provenance, where naturally shorter summarization or more abstract provenance yields less informative explanations. So we are now considering several extensions to these works. One of them is incorporating LLMs with natural language explanations and making the natural language explanation system usable with LLMs as well. And the second is a different privacy criterion for provenance, whereas in the first work, if you noticed, I didn't mention it by name, but the privacy criterion was based on k-anonymity. We can also think about other, maybe more robust criterions like differential privacy for queries. So thank you, everybody.
Thank you, Amir. Yeah, Val has a question.
Amir, so I apologize if you had an example in the first part of your talk in which you actually had some provenance that had a coefficient. I don't know, something like, think of a Boolean query whose provenance is 2p squared or something like that. If there is, so how do you treat it in the natural language explanation? What do you say about that coefficient?
So if this is a coefficient, that would mean there's a self-join, right?
No, not necessarily. It may
you mean a coefficient in
mean
the...
that you have a project, like think of the query, a Boolean query. Does Amir Gilad have any Sigmund papers co-authored with Daniel Deutsch, right? And there are many, so you will actually get a whole bunch of them, but you only track the fact that you maybe only track the fact that your co-author is Daniel or something like that. So you can have something like that even without a self-join.
Yeah. So I think in this case, we would separate we would basically write it out as the full assignment without the coefficient. So write out the full expression without any shorthand writing with coefficients, and then factorize it.
In some of your explanations, there were numbers like Junyang had 64 papers, and so that 64 did not come via this route.
Right. It came via a summarization of the number of values of the same type.
Thank you.
Okay, so let's take a break because we are running late, but we will start the next session on time at 11. So Benny, Brett, and Amit, Daniel, could you be back like 5 minutes before 11 Pacific, please? Okay, thank you. And let's thank the speakers again.